when we talk about rotations and attitude, we have to deal with a lot of different possible convention choices. And what perhaps is one of the most confusing of these choices is the difference between intrinsic and extrinsic rotation conventions, which is something that in particular applies to the sequence of Euler angles. So, you know, to describe an attitude, you generally need 3 Euler angles, and the sequence of these Euler angles do matter. So then we can compose the Euler angles in an intrinsic or in an extrinsic sequence. In the extrinsic sequence, which is what you see on the top here, you are rotating the whole coordinate system with every Euler angle rotation. And this is the situation that you typically have in mind if you think of some kind of vehicle, which you're first going to rotate it in terms of yaw, and then you might rotate it in terms of pitch, and then you might rotate it in terms of roll. When you do these motions, you are rotating the coordinate system along with the vehicle. This is what you see here. The yaw rotation gives you a new y-axis around which you're going to do the pitch rotation, and then again you get a new x-axis around which you're going to do the roll rotation. And this is mathematically very inconvenient because we don't really want to have to think about what these new axis of rotation are. So the other convention here is what we might call extrinsic rotations. And in the extrinsic approach, the coordinate axes are fixed. So you are simply using a sequence of rotation matrices that all work in the same coordinate system. So clearly this is much more convenient to work with. And then what is nice is that the extrinsic sequence is equivalent to the opposite extrinsic sequence. So we can use the extrinsic approach instead of the intrinsic approach. And this raises the question, how do we know this? So I'm going to give a proof of this identity. So let's start with the y-axis. We have to deal with this rotation matrix and this rotation matrix, and we want to get this modified rotation axis out of them. So for the y-axis, rotation, we can write it like this. So this is the rotation on the modified y-axis on the left-hand side, and then on the right-hand side here, of course, I have the rotation matrix around the z-axis. Then I have a rotation theta radians around the original y-axis. Then I have the inverse rotation around the z-axis. Okay, so where do I get that from? Well, let's make a simple illustration to draw what's going on. Let us now think NED coordinates. So the z-axis is pointing inward towards the blackboard. And then I have a vector v. Then I have, let's say I have that psi is about something like 20 degrees. So then my modified y-axis might end up here. dy marked is equivalent to this rotation matrix times the original unit vector in y direction. Then, if I now take the inverse rotation, so now, which should be minus 20 degrees, and apply that to my v vector, I'm going to end up here, about. So the point here is that when I rotate this v vector around the modified y-axis, then it's the same as rotating this vector around the original y-axis. So this is y. So first then I have this matrix that is popping up here, and then I do the y rotation, and then I transform back with the inverse of this matrix. So then let's do the x-axis, same principle. So now of course I first have to do the z rotation, and then I have to do the y rotation. So meaning that I write the y rotation first. Z rotation, then I get the x rotation around its original x-axis. And then, the same manner as we did here, now I'm going to have the inverse rotation matrices. And then I want to get rid of this modified y-axis here. So then we get some more nitty-gritty details. Fast. Now I have the inverse z rotation. Then just keep out this part. So then I have the z rotation itself. Then my x rotation comes. Then I have to do this part. So inverse z rotation. And then I have to take this part and invert it, which means I'm going to get, first of all, the z rotation. Rotation inverse. And finally the z rotation inverse. Then I can cancel quite a few elements in this. This is what makes this work. So it seems to have some obvious candidates. this one looks fairly obvious. I guess that is how much I managed to cancel. This one, and these two. So it's a little bit disappointing. I didn't manage to cancel away more. I'm aiming to get something like this, but all hope is not lost yet, because I can see what happens when I try to multiply this one and that one together, and hopefully then I can make this simpler. I want to have an expression for the rotated axis, my basis for the coordinate system. And then I'm going to insert what I had on the top. So for the x one, I'm going to have these things from down there. Then I'm going to take that stuff from my y rotation expression. And finally, I have this rotation matrix from over here. That's the last thing and all of these matrices are then going to multiply the original coordinate basis that we had. So what can we do with this? Well, we can do more cancellations, hopefully. Let's see. These we can cancel out. Start with more. Yeah. These. These as well, so then it doesn't look so bad. So then we have finalized the proof that the intrinsic rotation sequence is the same as the inverse extrinsic rotation sequence. So while this might perhaps seem fairly obvious, it's nice to have seen the mathematics with all the matrix multiplications to be able to rest assured that this works whenever you end up in a situation where you're trying to debug this strange sequence of Euler angles that don't work out the way you expected them to work out.